the Laboratory of Mechanics of Swiss Tunisia. The present work is entitled Modeling and Numerical Analysis of the Damage-Induced Compressibility Effect in Laminated Rubber Bearing. Bridge bearings are devices used for transferring loads and displacement from deck of the bridge to the piers of the bridge. The laminated rubber bearings are used because, in order to avoid damage to avoid transferring damage when the bridge is subject to thermal expansion or vehicular motion, even for transferring loaded to piers. The laminated rubber bearings are mainly composed of labeled rubber-like materials and steel molded as a sandwich material. The use of the labeled rubber-like material is because of their ability to absorb and dissipate energy without transferring harmful stress, and because they are known to undergo large elastic strains and they exhibit a highly nonlinear behavior, hyperelastic behavior. Commonly, the labeled rubber-like material made for bridges are neoprene materials, and some recent studies report that these rubber-like materials exhibit compressible hyperelastic behavior, and that a volume variation occurs during the damage process. Thus, modeling as accurate as possible the complex operating conditions combined to the nonlinear mechanical behavior of such elastomeric structure component is very important task for numerical computations. For the rest of this presentation will be split into three main topics. I will begin with proposed model to model this behavior. Then the second topic is a kind of an illustrative example applying this proposed model, which is the rubber bearing. And finally, I will conclude with some findings and some future works. The proposed model is based on the thermodynamics of reversible processes, whereas it is based on state variables. For this case, we have only two observable state variables. The first one is the left Cauchy green tensor, and the second one is the damage, which is isotropic. We adopt also here the multiplicative decomposition of the gradient of transformation into spherical and distortional parts. And here the barrel tensors are with volume preserving deformation, while the transformation of Jacobian accounts for the volume changes. The this proposed model is split into a spherical part and a deviatory part, where K denotes the compressibility moduli of the material. J tilde is the effective variable of J, affected by damage induced by compressibility. Here, G of T is an increasing function of the damage, and gamma is an intrinsic material parameters which have a value between 0 and 1. W0 here, the deviatory part, is the undamaged material, the deviatory part of the undamaged material, and capital damage here with 1 minus T. We choose Monnier-Veblen potential as an application here for this model. This Monnier-Veblen potential is split into a spherical part and a deviatory part as given by the system of equation here. And the damage evolution is described by the convex of non-damage that is available at any time of the loading history, F, here, where Y is the thermodynamic damage force that could be split also like the potential into a spherical part and a deviatory part. And QD is a positive increasing function of the damage given the size of the damaged surface and the deformation space. Here, Q0, D0, and N are material parameters. And the pseudo potential of dissipation, YD point, remains always positive. That is determined by means of the closest Joule inequality. The integration of the damage evolution is done with the normality argument and the consistency condition, f equal to 0 and f point equal to 0. Here, delta point is the Lagrange multipliers. This proposed model is then implemented in the Abacus software implicit. This software implicit platform needs, it's an iterative scheme, like the Newton-Raphson scheme, that needs the calculation of the tangent matrix, which sometimes difficult to identify and to calculate, and also that the tangent matrix must be consistent with the integration scheme. As an example, an illustrative example, we adapt a common shape of the rubber bearings, which is a cylindrical shape, here represented with 3 layers of neoprene materials and 2 armatures and rigid material. Because of the geometrical symmetry of the structure, only half of the structure is modeled and represented. And the loading conditions consist on 2 steps. The first one, we apply a compression loading up to 24 tons along the F direction in the first step, and in the second step, up to this pressure F, we apply a 10 mm shear displacement imposed in a second step along U direction. The structure is meshed using a 3-dimensional hybrid quadratic bricks, C3D 20H elements. And this configuration is for two types of material, an A material and an equivalent material. The A material means that the 3 layers of the neoprene material are the same, with the same compressibility, with the same coefficient from the Maha law. And for the equivalent material B, C, and D, here we have the material is neoprene, but the compressibility moduli is different, and the parameters of material are different. To reach different compressibility and different parameter of monomer material, even with the same concentration of ingredients, but when we change the curing time and temperature, we have different compressibility moduli for the same neoprene material. We try to master the length between the macromolecular knots, and we have different compressible moduli. Here I present the geometric loads and material parameters of the laminated rubber bearing used during the simulation. For the neoprene material, the compressibility material, for A material, for the equivalent material B, C, D, not the same initial compressibility. Here is the radius of the rubber bearing. A is the width of the neoprene layer, B is the width of the steel. F is the applied force, 24 tons, and U is the displacement. For the rigid material, we have Young moduli and Poisson ratio. For the damage parameter, we have here the intrinsic parameter that denotes the damage induced by compressibility, and here the parameters for the damage evolution law, T0, T0 and N. We present here the damage distribution and the 3 layers of laminated rubber bearing for the A material, and here for the equivalent material. We can notice that there is a disparity and a concentration of the damage here in the lower band near the interface with the frame, while for the equivalent material, the damage distribution is better homogenized, and the value, even the value of damage is lower. We can see here for the non-coupled case with damage, and here the stress with the coupled case with damage. For the coupled case, the stress decreases, and here for the damage evolution, we have in slide lines the A material and in dashed lines the equivalent material. The damage for the A material is higher, and the discrepancy appears between the equivalent material and the A material appears up to 10% of elongation. Here we represent the damage evolution versus the time of resolution for the same integration point. We find that the damage changes position from compression to shear. This could be attributed to the low drop of the stiffness, the overall stiffness, which is sensitive in shear than in compression. And in order to better homogenize the distribution of damage while maintaining the stiffness unchanged, we propose another geometrical edge, which is the chamfered edge. Here is the mesh view with the chamfered edge and the 3 layers of neoprene. And here we find that the damage distribution in the 3 layers of the laminated rubber bearing using the A material is better homogenized. Even the values of damage are lower. As a conclusion, we have developed a numerical tool based on the finite element method to predict the behavior of the damage-induced compressibility of a hyperelastic structure subject to monotonic loading, compression, and shearing. And we find that the damage prediction could be improved using an equivalent material instead of the A-type material. And a new approach is adopted to better homogenize the damage distribution by substituting the exterior cylindrical shape with the chamfered edge while maintaining the initial A-type material. For future work, we will focus on the extension of this formalism by taking into account the stress softening, the high hysteresis loss, and the cyclic softening, and the random fatigue case. This will enable us to predict the fatigue strength of this new laminated rubber bearing. Thanks for your attention.
Thank you very much. So who wants to start the discussion?
Correct me if I'm wrong, but you have done a 3D model, right?
What?
You have done a 3D model,
Yes.
okay? I suppose that the criteria that you have used to increase the damage is based on stress, correct?
Yes.
Is it principal stress? The reason
Strain energy. Is it strain energy?
strain energy.
Yes, it's why you are.
But you have coded the damage in using subroutine in abacus. So you have integrated it into stiffness matrix 1 minus d. And my question therefore is, if you do a 3D model which is based on strain energy, for instance, that means you have damage matrix, 3D damage matrix, okay? Therefore, if you have combined loading conditions, how do you specify, because here you have presented only one damage parameter, how do you specify the implementation of each of the damage parameter in your damage matrix? And if you have combined loading conditions, how do you take into account the rotation of the increase of damage into this damage matrix?
This formalism, the hypothesis is the compressibility effect is taken into account, but the damage is isotropic. So rotations and we are
because it's well known that once you have a damage tensor given, if you change the loading condition, you cannot rotate it. It doesn't work. I mean, you cannot combine mode 1 and mode 2 on the same point. Because if you diagonalize your tensor damage, it can lead to negative values, which is not possible.
Yes.
Okay, so.
And we don't take into account the isotopic damage.
Do you have some tests on this material?
Yes.
On the component itself, in reality, how does it break?
No, in reality, no. We have in our lab, for instance, C10 identification of C10. It could be axial tests. And we have a double shearing test with M&MoCS. In fact, we are not it's just an example. We are we need to find many properties like the identification of these parameters, and also today we are taking into account the spring-induced crystallization of the materials or the diffraction.
But are you sure that the damage takes place in rubber, or is it at the interface between the
for the chamfered edge, the damage in the rubber. But for the
interface is very strong. It's glued, or it's
it's glued, yes, and in the simulation tight.
Okay, but in reality, I mean,
in reality, for the cylindrical shape, the crack is between the interface,
at the interface or in the rubber?
At the interface for the cylindrical shape, but for the chamfered edge, it's in the rubber.
Okay, and it's better for the.
Yes.
Question? No? If not, thank you very much again.